Okay, this is 16.5 triple integrals, and we're gonna do the triple integrals for cylindrical and spherical coordinates, and that's pretty awesome. So yeah.
Yeah.
Yo. So let's get through this because this is important. Okay. So we can describe R3 with more than just rectangular coordinates, right? So in rectangular coordinates, oh, you know what I'm gonna do? I'm going to be smart and I'm gonna label this stuff. So, guys, okay, please bring it in. We've got a lot to get through today. So rectangular, as a reminder, why did I say rectangular? That's not even true. Cartesian description of R3 is going to be the set of points X, Y, Z, where we know that negative infinity is less than X is less than negative positive infinity. And what do you think is going to be true for Y and Z? Same thing, right? That's what we mean when we're talking about R3. Is X, Y, and Z are all varying between negative infinity and infinity. So that's all of the points. You can get every single point in R3 in that description. That's Cartesian. So this is what we've been doing since pretty much the start, right? We just assumed that to be true. I haven't never formally written that out, but the reason I'm formally writing it out is so you can see the parallel structure and how we're going to talk about these other ways. And so the cylindrical, I want you, when you see a cylindrical, I want you to think of polar, but now plus Z, basically. So it's exactly the same as polar, but we just throw on the Cartesian Z.
So on the Y, you also have negative.
Oh, I appreciate you for catching that. Yes, negative infinity, negative infinity. And so now we can also describe the R3 space. So what are the first two variables for polar?
R and theta.
Yeah. R and theta. And so then all we're doing with cylindrical is we copy polar, but then we add the Cartesian Z.
Mm-hmm.
And then, so R varied, do you remember what R was varying between? Zero. Well, zero is something, right? So zero is less than R, but if we want to sweep out all of the space, we let that go to infinity. Theta is actually finitely bounded between what? Yeah, because that's just rotating around. And then the Z is the same as in Cartesian. Why? I need help. Okay, let's see. Minus infinity is less than positive. And then we're going to also talk about something called spherical. And when you think of spherical coordinates, I want you to think of a sphere, which isn't too difficult to do considering how it's been named. And we're going to call this a rho phi theta. I'll elaborate much more on this later. But rho phi and theta, where rho is going to vary. Rho is essentially R in the cylindrical. It functions the same way. It's the distance away from the origin. And so 0 less than equal to rho is less than infinity. And then the phi, we'll talk about what these actually mean. It's going to be 0 is less than equal to phi is less than equal to pi. And theta is going between 0 and 2 pi still. So 0 theta is equal to 2 pi. So don't worry about what the phi is, but we'll talk about all of that. I'm just showing you this is it. Okay, for triple integrals, there you have it. The three ways we're going to talk about R3. So let's step back to cylindrical coordinates. And I'm going to draw pictures because pictures are actually kind of fun. Okay, now I gotta figure out how I'm going to draw this. So here's X. There's Y. There's Z, okay? And so what do we mean by, how do we identify the address basically using cylindrical coordinates? So what's going to happen is if I choose some point like right here. Okay, and so this is a point, that has some r value, some theta value, and a z value. Now, the reason why this is pretty much the same as polar is because we're going to look at its projection in the xy plane and basically see, okay, well, right, so depending on how far it is, so say this is its projection. So if we were to shine a light down and look straight down, that's where it would be. And so here is that, right? So this is how far we've swept over theta. So if you're looking at this top down, it's the same thing as polar. How far did you swing over off of the positive x-axis? And then on top of that, we're also interested in how tall this is. So this height is what the z is representing in the coordinate, right? So if swept around a certain amount, we've gone up a certain height. Now, how far away are we from the z-axis? Well, that's given by that is what that measure is. So that's what this is. So it's the very same as polar, but now we've just lifted it off the x-axis. Hi, Chelsea. We're doing the cylindrical and spherical coordinates today. And this is just currently what's on the board is a description of the 3 different ways you can describe that. Okay. Does that make sense? Did I draw that well enough that you can kind of visualize like the concept of if now I choose a different point, I start from the x-axis, I first swing onto where I'm going, extend out how far I am away, and then raise up to how high or how low it is.
Yeah.
Yes.
So that's the same length as C, right? Like the same the dot.
This?
Yeah, it's the same as
Z.
yeah.
Because that's telling you how high up Z
Yeah.
is. Yeah. So like this mark right here, if I were to tick mark this, that would be. I should probably use Z not just to indicate that it's like, but I'm trying to show that these are variables. So as I drag this point around, that description is still valid. And just we're changing how far we're sweeping around, et cetera, et cetera.
Does theta always start from the x-axis?
Yes, very good question. So same thing with polar, is that you will always start sitting on plus x and then start swinging around like that. So, you guys use this in, I don't know if you ever did like Lego robotics competitions and stuff like that, but it's essentially where when you're trying to make like a crane, I remember there's a crane project. We didn't use cylindrical coordinates, but the concept would have actually been done much easier because it was a base crane that would rotate 365 degrees, and we were trying to find a way to basically make it go up and down, like choose the height of the crane to pull things. And that's basically all this is. This is the crane. You can think it's pivoting around and it's spinning around in the base to see where am I going, how high do I need the end of my crane point to be. The Z is like, okay, so we need it to go up, we need to go down, and then R is how far are we extending out the arm versus how far we protracted. Okay, so you can sweep out all of the points in R3 that way. So what kind of shapes are going to be easier described with this very specific set? Well, things that happen to have height and also go around, like cylinders. So things like cylinders and cylindrical shells, tubes, pipes, even sometimes planes, half planes, and cones. Cones are so much easier done in this method of describing what space is compared to, say, partition. Okay. So this is, I'll label it so that we at least know what we're talking about. So this is our cylindrical. And then I'm going to put over here the spherical. So what we mean when we're describing R3 and spherical coordinates. So a similar setup here. Let me put the x-axis, y-axis, the z-axis, and then I'm gonna have some point kind of here. And so we're going to call this point given by rho, phi, and theta. So let's talk about what these actually represent. I want you to think of the rho as kind of the concept of R, except for now, instead of being a distance from like the Z actual axis to the point out, it's going to be from origin. It's always going to be coming from the origin. So this distance out to the point is what we mean by rho. So literally from origin out to point, that distance right there is rho. Does that make sense? Now, how else are we gonna get the other parameters of it? So if I like bring this down, also, just so you know that this is truly projection, I'll make a little 90-degree mark, so you know that that's coming down. So in the same way, if we see how this comes down into the XY plane, say here's where it would be projected, right? If we were to look straight down at it and then see how far we swung around to get there, this is an orthogonal, so that's 90 degrees. What do you think that angle is going to be called? What have we been calling it? Yeah, so we don't change things for no reason. If it's the same idea, we keep it the same. So that's going to be theta. But now, instead of how are we going to get, basically, how do they get off of the z-axis? And what we're going to do is we're going to use this angle called phi, which is going to start. So just how theta starts at the plus x and starts sweeping around like that. What the phi is going to do is it's actually going to start standing up, aligned with positive z, and it will fall down. It's the angle measure of how much you have to fall, by what angle you need to fall to be leaning far enough down to get to the point. So it's really this angle right here from the z-axis down to the point. That's what we're measuring with phi. Does that make sense? So now does it make sense why phi is restricted to 0 to pi, right? Because here, 0, if phi is 0, that means we're just up. But as I increase phi, I'm going down. If phi is now aligned with, say, the xy plane, that's been pi halves, and then pi. Now, why do I stop at pi instead of loop all the way around? Well, basically because it's redundant. Because I can just increase my theta to spin us around to the other side and then do the same exact thing and go down. So to be most efficient, so we don't double count any points, we just stop it at pi. Make sense? Okay. So this is, if you imagine that, if you design like some sort of a lever where it's got a single joint that pivots around 360-degree axis, and then the arm comes down on some sort of a control. So you can reach down and scoop things. And then you can also extend how far you're probing with the row. So all these are the two, let me put down this as spherical. So it is spherical. Okay. The reason why it's so important and I'm spending so much time on the visualization of it is because when you actually really grasp how what it really means to be that point in cylindrical, or what it really means to be to achieve this point in spherical, that's the hardest part, is setting some of these shapes up. Because now, if I ask you to describe, say, like a sphere with this, you would say, okay, well, what am I sweeping around theta? To get the whole sphere, I need to go all the way around. So there's my go-to part. On my row, well, the row is just exactly from the origin out to the end. If it's just a sphere, that's just going to be a constant, right? And then what's my phi going to be? Well, if I want the entire sphere, I want to start here, but I need to make sure I sweep out every single thing from top down to bottom. That's going to be 0 to pi. So inherently, by calling this spherical, we've essentially kind of described sphere, right? With just a way. So it views R3 as this infinitely expanding sphere. Whereas Cartesian views R3 as an infinitely expanding box. But yeah, okay. We good with that? Thumbs up, this is good. You can see it, you can visualize it.
Technically, you do for the
Yes.
0 to 2 pi and theta is 0 to pi.
Actually, let me consider that for 1 second. So if you go all the way around that way, so sweeping, but then only going, got to that side, which if you had swept around. I think that the issue is you're missing the other side of, so you're missing pi to 2 pi theta. So you could rotate everything through the hemisphere through the first quadrant and the second quadrant, or octant at that point, because we're in R3. But I'm pretty sure even if you're sweeping around, you're missing, if I was on XY, stopped there, but I let it go all the way around. Okay. No, yeah, actually that would work. Because you could effectively reach all of the points behind. Because if you're saying let this go to 2 pi and then make this stop at pi, yeah, you could. The reason why we don't is because do you see how the choice of calling this phi and the choice of calling this theta is arbitrary? And why change up the system of theta being all the way around? Because that's what we've been doing for the last 3 coordinate systems. So it's more a matter of convenience in terms of continuation. What you said is completely fine. I'm sure there were mathematicians that said, hey, guess what? We could be silly and we can do this. But then science came along and said, well, we already have a system that's really nice. And so the let's actually name and convention. So there's lots of things like that, just unspoken assumptions and convention etiquette and math. But yes, that was a good question. Anything else on this stuff?
So that's so on this cylindrical, it's a cylinder with respect to like the z-axis, right?
Yes.
Okay.
Yeah.
And how would you get it to change if we wanted with respect to the y-axis, or really just move with respect to the z-axis?
Yeah, it depends on the equation you're using. So it depends. At some points, there are certain, that's why we have the quadratic surfaces originally given in Cartesian. But you can use the translation equations, which I'll put up on the board later to get back. Yeah, but that's a good. Because you're thinking in the right direction. So let's start going in the right direction. Good to erase. Yeah. You'll know when I'm having more fun with the mathematics that we're doing with the less formal I give you. Freaky. I call there's funny algebra, goofy arithmetic, all sorts of different things. There's no reason to call it something intimidating and scary because people are already scared of it. So, do I need to give you those? No, I don't. And I'm not going to. Okay, so transformations. Transformation equations. This is going to be for cylindrical, okay? So for cylindrical, again, cylindrical is polar. That got upgraded with the Cartesian set, okay? So this is not going to be a surprise to you that r squared is going to just be x squared plus y squared, right? Same thing. This is just trigonometry review. Tan theta is the y over x ratio. Okay, so nothing's new there. Z, believe it or not, is Z. And actually what's funny, the irony of saying that is earlier in the semester, we talked about defining equals from set theory. So really know what Z is Z. Yeah, it's true. All points, basically the subset of the relation that takes the Cartesian product of R onto R, such that the coordinates contained are in the form that Z and R. Okay. And then to go the other way, X described in polar is what? Yep, and since that's how it is in polar, that's how it's gonna be in cylindrical. Why? Cylindrical is just polar plus Cartesian Z. Y is going to be what?
Theta.
And Z is going to be what? Yeah, nothing changes. Same thing. Okay. So, the transformation equations for spherical are a little bit more complicated. I'm going to write them out first, and then I'm going to point out some patterns to you and teach you how to think more like a math person. And sometimes, believe it or not, thinking like a math person is a little bit more useful than being practical all the time. So, extending the idea is something we've talked about a lot in this class. And especially in the idea of moving from set 2 dimensions to 3. So if this idea of distance from an origin originally started as a radius in the plane, this isn't a radius per se, but it's a distance away from an origin now contained in R3. And so what do you think is the concept different? No. So sure, we might have to extend it by a dimension, but what's it going to be? What's rho squared going to be? If we know that the cylindrical r squared is x squared plus y squared, what is rho squared going to be?
Cosine theta squared.
Well,
No.
we're going to start with the x squared and the y squared. What are we missing? Spherical comes from the word sphere. That's the equation of a
Sphere.
Sphere.
okay. So it all makes sense. Now, to find the other stuff, I'm going to put the really frustratingly ambiguous use trig to find, yeah, I honestly I could just say use trig and then everyone to find phi and theta, because that's always going to be contextual to your shape. There's no, honestly, the general rule for it would be more scary than just saying in context, it'll always be easy to look at what's happening. So this is not a cop-out. This is actually just saving your eyeballs from seeing something horrible. And also I'm not willing to write it down. So now X, I'm just gonna write these down and then I'm going to show you the pattern because I think that's going to be the most effective. So rho sine phi cosine theta. Y is rho sine phi sine theta. That is rho cosine phi. Okay, so when you're memorizing stuff and then suddenly there's just a bunch of garbage, that's not a lot of fun. Okay, and so the idea is, how is this still an analogous idea to my lovely simple r cosine r sine? Okay. Well, the r and the rho can be thought of analogously. So we have the rho cosine, we have the rho sine. So what's the sine phi going with? But I want you to see this pattern. If you treat rho sine phi as r, it's the same exact thing. So don't memorize more than you need to. Memorize this, and then the only thing you need to memorize for this is that r is now in spherical going to be understood to be rho sine phi. Because now you just plot that in there, which is the place that you're doing your transformation. See that? Now, how do I know that r is equal to rho sine phi? Well, do you guys still have your pictures from earlier in the notes? So pull those up, okay? Take a look to the relationship between the z component, basically. So remember, compare this the cylindrical together. I should have left the picture. Okay, you know what? I'm just right there. Do we need this? Or can I erase this stuff?
Yeah.
Okay, I'll erase this. So what's going on is if I have that x, y, z, choose a point. Wow. Oh my goodness. 90 degrees. Theta. And if I want to see this as cylindrical, instead of going from the origin up, I'm going to go from the axis up, and that's going to be r, right? But I'm going to impose both coordinate systems on the same picture, which I'm now realizing is ridiculous. I made this so small, so let me make this bigger. They can actually take up this space. So x, y. Okay, so here's a point. So cylindrical r. The theta is the shared thing, right? That's the same. That's cylindrical z, but which is the same thing as Cartesian z. So keep that in mind, right? And then also, I'm going to impose in solid lines the spherical version. Okay, so you see dotted is going to be for the cylindrical, this is going to be for now, so that's rho, and this angle dropped down is phi. So I want you to do just a little bit of trigonometry here. Rho. Here's the angle phi. The relationship between that for this is essentially that magnitude where you're taking the magnitude of that hypotenuse, the rho, sine, because when you do so kata, you have the opposite, right? Oh, now it works. And then there's another triangle in the other direction. So why on earth is z suddenly cosine of phi instead of sine of phi? Why are we using the other? Yeah. Because instead of going with the opposite side, we're taking it as adjacent. You see, now it's adjacent. Now, how do I know that this is phi? Because this is a straight line. So So that's when it says use trig. Just take the picture as it comes, okay? It's a lot easier to see it that way. So these formulas are very closely related to this, which all comes down to, do you know the relationship between how we're actually sweeping out these coordinates? So do you see for yourselves why this still works? We've essentially made polar extend up into 3 dimensions without needing Z. And we're doing it through this. We're using it through the cosine component with respect to how far you are away. So this right here, a lot of fun. I had to teach myself this. Okay, so let's see, it's 1/28, which is almost perfect. So I'm going to show you the definitions of the integrals and then we'll do a problem. How about that? Yeah, the first time I drew this in a lecture, it was not that pretty. It's been practice. Practice, practice, practice. They say practice what you preach. So to the math people, I say practice what you teach. Because it will make a difference. Comes to. All right. Let's see. Actually, you know what I'm gonna do? I'm gonna just freeball it. Okay, memory. If I can do this for memory, and I'm a Rust bucket from 2 years ago, you guys got this. So from cylindrical, in the Riemann definition, we're going to go a triple integral over my region D given in cylindrical of a function f(x, y, z, dv). We know this is going to be a limit where the deltas are going to 0. Now, what are we doing? Well, we're taking a limit of a summation. It's going to be k equals 1 to whatever n is. And now we have the function here. Now, x, translate that to cylindrical. What do you got?
R cosine theta.
Right, r cosine. So I'm going to choose some r sub k in the partition times cosine of a chosen angle sub k in the partition. And then what's y?
Or sine theta.
R, yeah, choosing an r, sine, choosing a theta. And then what's z?
Z.
Z. So we choose a z. Now, dv. This is going to be important. So in polar double integrals, what is dA?
RD theta.
Good. RD theta. Do you think that's suddenly going to go away if we throw on a third Cartesian going up? No, it's still there. So we do the delta z first, but we're still going to have that r, that chosen r, but now we have delta z, delta r, delta. Because this constitutes that change, that Minecraft cube of volume that we're summing up. And this is how we have to happen to do it if we're going to change over to using an extended polar.
Is that R K to the
RK star, it's a Riemannian convention to notate the selection of an R inside of that partition that is arbitrarily getting smaller, and that's what we're taking a look at. Yeah. Okay, and then now let's do spherical. This is going to be slightly longer. And by slightly, it's almost like comedic how massive this thing is. So D, F, X, Y, Z, E, E. I'm having too much fun, guys. I miss doing this kind of stuff. A person can only memorize so much Greek vocabulary and write so many pages before you lose your mind. Okay, so k equals 1. And so now my function, remember the translation equation. So when I go from cylindrical up to spherical, that radius now becomes the rho, and then the sine component with respect to phi. So I get a rho I choose a rho sine chosen phi in the partition, and then x is going to be cosine overall with theta. So chosen theta. And I think you can see how quickly this is going to escalate. And so in the y component now, we still have the same r, right? So the rho sub k, the chosen rho with our chosen sine e sub k star. But now we're doing the y component. So instead of overall with cosine, we're overall with sine theta.
We just. Can we say like R equals the rho sign? That way we can just shorten.
But we're trying to construct the definitional form, yeah. Abbreviation is for the scientists to do, and that's why physics is simple mathematics. And then the Z is now we're interested in the cosine component of that angle phi to get the going up and down. So Z is going to be the rho, the chosen rho, with the cosine of phi. Boom. That's a lot. But it needs to be there. Okay, and so then this little delta V is going to look a little different. We're not going to derive this, so I'm just going to tell you what it's supposed to be. It's going to be rho squared sine phi. Okay, that's going to be how this works. It's going to be rho, instead of adding just an R, we're going to add rho squared sine phi. Rho squared. Oh, it gets funny really fast. Actually, let me put this in parentheses so that it's clear what's going on. So we choose this row, right? Row, and we square it, and then sine phi. And then we have the differentials for rho, phi theta. So delta rho, delta phi, delta theta. This massive honk is describing that volume change in spherical. Real pretty, ain't it? Huh? So when we look at these in their more integral forms, it's not going to look like this garbage. It's going to instead look just like an iterated integral with respect to your specific variable. So let me actually pull up the definitions you're going to need to have. And I'll just put them both on the same board, and then we'll close with the example. the very nice special example. Okay, but we good with this? I will not ask you to reproduce it on an exam because that would be something maybe past the caliber of an engineering calculator. But I will definitely have you do extra credit, yeah. Do the Riemannian and construction. Okay. All right. Theorem. All right, so we're gonna let that be over the region.
Is this raise the power from the?
Express in cylindrical coordinates. As, okay, so here's how we're gonna do this region D now. This region D is cylindrical. What are the variables for cylindrical?
R. Theta. Z.
Z. Okay. And then what we're gonna do is we're gonna bound R. Remember in polar, with the polar general regions, we basically had some sort of a lower function with respect to theta and a bigger function with respect to theta. Guess what? That's the same. So we have some g of theta less than equal to r less than equal to h of theta. And then for the actual theta value, we just restrict that between alpha and beta. And then for z, we actually do this, we just have surfaces with respect to x and y. So dxy less than equal to z less than equal to some h, x, y. Okay, so if that's the case, then f is integrable, very important, over d. And here's the iterated integral. So the triple integral over the cylindrical region of a function f x y z dv is, we do the theta last. So the order we're going to do this in is do the dz first, because effectively the dv is going to turn into dz dA. And in polar, dA is what?
RD.
RD
theta.
So in polar, dA is what?
RD
Okay,
theta.
so then if the cylindrical dV is dz times dA, then the dA is going to be the same. So memorize it like that. So we're gonna do the outside integral is alpha to beta. And then g of theta to h of theta. And then the surfaces first, because this is the j, this is the. And so x's are cosine theta, y is sine theta. H of x's are cosine theta, y is our sine theta of our function f, now written as our cosine theta, our sine theta, and z. Now, it's dz dA. Got it? dV is dz dA. So dz, and then what is dA in polar?
RD theta.
R dr d theta. So memorize dV equals dz dA. So in polar, what is dA?
RD theta.
And dV is,
TC
yeah.
DRD theta.
Yes, they can be interchangeable, but in general, this will actually just route the best. Yeah. Problem context will always win. Okay, in polar, dA is what?
RD theta.
Cylindrical dV.
theta.
Yeah, if you want to memorize that, it's just dz dA or dz RD theta, you can do that. But just know that for yourself. Okay. And then for spherical, we're gonna have to memorize a different little differential solve. Here, let f be continuous over the region T expressed in spherical coordinates now. Yes, actually, it's a little bit easier. Oh. Because spherical is such a, it's a more restrictive way to do it. So rho phi theta. And so now 0 less than or equal to g of phi and theta less than equal to rho less than equal to h of phi and theta. I leave that to your very, very developed, intelligent, God-given brains to see parallel between the treatment of rho and r. Now phi is easy. We just restrict it between some a and b. And theta is good old constant theta, always between all theta. Okay, so it's actually easier. And then f is integrable over d. And the iterated version of this integral is going to be, we have a triple integral over d f x y z dv. Here's the order of how it goes. It's always going to be, and from first to last, d rho, d phi, d theta. So on the very outside is going to be the stuff with theta because that's last, and the theta stuff is alpha to beta. Now, so if it's rho, phi, theta, phi is in the middle, and phi is going to be between a and b. And then, of course, rho is in the center. So we have the g of phi theta and h of phi theta. F of, and then of course, this is, not the prettiest thing in the world, but so we have, do you guys remember it? Say it with me. So we got rho sine phi. What's next? Is this the sine or cosine of theta?
Cosine.
Cosine of theta. Okay, once you see that, you should be able to put the pieces together for the y component. What is it?
Rho sine B sine theta.
And then what's the z?
Rho
What is,
cosine.
yeah. The rho cosine of which variable?
Phi.
Yeah, cosine component. Now, the dv for this, I'll put it up here. I haven't showed you it yet. So rho squared sine phi d rho d phi d theta. So you want to memorize dv equals rho squared sine phi d rho d phi d theta. If you say it enough, you'll convince your brain that you remember it. dv rho squared sine phi d rho d phi d theta.
It's beautiful.
Okay. So as a means of review, in Cartesian double integrals, what's dA?
dx, dy, or dy, dx.
In polar dA is,
RDR,
okay, Cartesian dV.
dz, dx, dy.
Right, so basically any combination of dx, dy, dz. And then the cylindrical dV is what?
dz, rdr, d theta.
And then the spherical dV is
Rho squared sine p
rho
d
dV theta. Okay, let's do this one again. Spherical dV is rho squared sine p d rho dV theta. Spherical dV is
Rho squared sine p d rho d p d theta.
Okay.
Like that.
So if you want to, if you ever like, if maybe you're more Baptist than charismatic and you in chapel and he's like speaking tongues, rho squared sine. I'm kidding. I'm sorry I recorded that. Well, you know, my Greek professor was making jokes about that. He's just like, there's main saw time method and then is the endings for or my time method. So it sounds like you're speaking tense when you're memorizing all of your primary and secondary verb endings for indicative mood. So, anyways, we good with this?
I need that last one still.
Oh, okay. And then because the only thing we have left to do is our little special spherical example. Because this is, you'll get to see, we can have ridiculously overpowered stuff to basically verify really simple formulas. We'll do volume at least, yeah. The and while people are writing. So in spherical, what is dV? Rho squared sine p d rho
d theta.
Okay, spherical dV is what?
Rho
squared sine p d rho dV theta. If I run into you on campus.
I need to fit. I need to fit. I will not answer that question.
You just, I object.
No, you will see me from the opposite.
So I'll be like, hey Diego.
But in that case, Diego, would you mind standing up for the class real quick? Everybody make eye contact with Diego and ask him, what is spherical dV, Diego?
What is so dV, Diego?
Okay, now everybody, spherical dV is what?
Rho sine p d rho d p d theta.
It's a row.
What I say? Oh.
Okay.
Okay. I'm good.
If any of you have like music classes or like production electives and you turn that into like a SoundCloud rap track, that'll listen to it.
We get extra credit.
Yeah. Plus 1%. Okay.
Plus 1%.
Okay. Are we good to erase at least the top?
Yeah.
Okay. Because then that way I can write what the question is. Okay,
I think a good beat.
everybody, in spherical coordinates, what is dV?
Because
you can see it. Okay. Okay, if I stand right here. Spherical coordinates dv.
Sine phi d rho dp d theta.
Good. Now do it with an Australian accent.
No.
Spherical coordinates dv. When I think I was. That's it. Like,
D rho dp d theta.
I love how you're sitting closest to my laptop. I'm gonna pick that one up. Okay. So here's a region. We're gonna integrate over this region, guys. This is our very special example for today because this is my personal favorite.
It's our only example of the day.
Rho b theta. Okay, so the defined by rho is gonna be a fixed r, which is positive, so it's a radius, and this is a subset of R3, right? So it's not all of R3, but it's just that region over here. Okay. Okie dokie. And technically, that's not really necessarily correct. Because I don't want just the out, we're not doing a ping pong ball, we're doing like the actual thing. So I need to make this less than or equal to, right? So all of the rows that go up to the row are the R. Yeah, so long as this is, why did, you know what, this is horrible, let me just rewrite this again. We're gonna do this. 0 less than or equal to rho less than or equal to R.
That works better.
Okay. Yes. Yeah, this is meta. Okay, everybody go with this? So what shape, what is this? Yes, so you guys allegedly know what the volume of a sphere formula is, right?
Yeah.
What is it? Everyone hear that?
4 3 5.
Okay, so we know the volume of the sphere with radius r is 4/3 pi r cubed. We can verify this with cylindrical coordinates, okay? And spherical coordinates. So here's how this works. We can say, all right, the volume of a sphere, or which is basically the volume of this region D. Make sure you understand this concept very clearly. Its first step is that when you're finding just the volume of the region, the function is now just one. We're integrating over an integrand of one because we're only interested in the volume over a three-dimensional region. Does that make sense? So in the same way that if I just wanted the area, the double integral, I would just have double integral over r dA, right? I don't add something into the integrand. Don't add something to the integrand because we just want the volume of the given region. The region's already in 3 dimensions. We just want to integrate over the integrand of one. Make sense? So make sure you show this. This is important.
Is that partial or full?
No, this is just meant to say you're integrating over your region with respect to itself. You're getting the volume back of your region. Okay, but then we can actually express this as an iterated integral, right? So, what is, okay, so, and there's a reason I had you chanting for no reason, was spherical dV is what?
Rho squared sine phi d rho dp d theta.
What order are those differentials? Say it again.
D rho dp.
So what's on the furthest outside?
D theta.
Okay, so what are we doing for theta if we're doing sweeping out a whole sphere?
0 2 pi.
I do genuinely, for your own sake, hope you're taking good notes on this example. Okay, what about that phi?
0.
Any other mental reasoning behind just because it sounds right? Yep. And then what is that one gonna be?
0 to r.
Not to be confused with like the variable r, but it's just a constant for the radius. What's the integrand again? Right, it's just one. Now, I emphasize, what is spherical dV?
Rho squared
sine
sine
p d rho dp d theta.
Got it? Okay, so since we're doing rho first, sine phi is gonna be a constant. So pretend like that's the number 4 or something. Okay, so that's not gonna be doing anything when we do that the very middle of this, 0 to pi, 0 to pi. So when we anti-differentiate, we're gonna have 1/3 rho cubed, right? See that? Because we raised the power of rho by 1, divide by the power, rho cubed divided by that 3. Now, sine phi is being treated as constant because we're doing d rho as the variable. We're doing integrating with rho's. And then the rest is chilling, d phi, d theta. Sine. Oh, I forgot to say what we're evaluating. We're evaluating this on the limits. And so that's going to give 0 to pi, 0 to pi. And honestly, what I could do, because I know that these are going to be constant, when I put in the r, it's going to be 1/3 r cubed, right? But then 0, if I put 0 in for rho, it's just going to make everything 0. So we only have when we plug in the r. So I'll actually pull the constant out because it'll make it easier. And we'll just do 1/3 r cubed on the outside, right? So we have 0 to pi, 0 to pi. And then now all that's left is the sine phi, right? Because that's what we have to integrate next. Sine phi d phi d theta. Okay. Thumbs up if that tracks up to this point.
Yeah.
And what I mean by tracks is if you started from this point, you actually could have gotten to that point. Cool.
Yeah.
And if you can't now in lecture, that's fine. Just make sure you can do it for next week. Okay. Now what we're gonna do is integrate the sine phi, right? So we still have the 1/3 r cubed hanging out outside. We have the 0 to 2 pi outside. Now we're anti-differentiating sine. Don't mess the sign up on this, please. It's just minus cosine. So make sure you change it to negative. And it'll be 0 to pi d theta. The integral actually, so there's a few famous integrals. One of the famous integrals is 0 to pi of sine. That's 2. So honestly, if you recognize that and just say that's 2, more power to it. But I'll show the antiderivative. But this is just going to be the 2/3 r cubed. We still have the 0 to 2 pi. But notice we've taken everything out. The only thing that's left is d theta. Now, what do we do when there's nothing in here? When the calc 1 integral? Well, the antiderivative is just the variable itself. And so when you take this minus this, that's what this is going to end up being. It's 2 pi minus 0. So we take 2/3 r cubed times 2 pi minus 0. Which, believe it or not, is 4 pi thirds r cubed. End of problem. Okay. Questions about okay, let's break it up this way. Questions about the region, the way we've described the region. Okay, questions about volume for a triple integral being a 1 is the integrand. So integrating dv. Okay. Questions about the limits of integration. 0 to pi, 0 pi, 0 r. In spherical, what's dv?
Just sine p d rho dp d theta.
Okay, so then there's no questions about that. There we go. Questions about why the sine phi is hanging out, and we do this 1/3 rho cubed.
Constant.
Good. 0 to r makes sense because that's what we're integrating over it. Why can we pull this out? Good. And then that integral happens. Cool. Okay. So this is a problem that represents spherical coordinates pretty well. If you want a way to practice, just go through it, do it for yourself. And then also you can mess around, right? You can say, what if I only want the hemisphere? Right? Will I get that? So what are we going to change if we only want the top hemisphere?
0 to 5.
Well, so that's gonna change the horizontal hemisphere. I'm talking if I want like a snow globe. Yeah, I'm gonna change this to pi half. Instead of going all the way down, I'm gonna stop. And that's what I'm spinning around. Let me think. The reason why I like another reason why I like these is because there's certain regions that are really weird. So you can find the volumes of snow cones now. Because essentially, if you're taking around these weird, so like spherical sectors, portions of globes. So if you were to cut into those kinds of things, it does just adjustments on how far you're choosing to sweep around, and also adjustments on how far you're willing to like bound this kind of stuff. So if that's good, you're free to go, and I'll see you on Monday. On the lab that was due, I just pushed it back because I forgot that there was another break coming. So then it's all fine. So yeah, I think the next is it that takes. Yeah, it would be next. That's due on not today but Friday. So yeah. All right, you have a good one.